uncertainties. So what is that types of uncertainties? Maybe parametric uncertainties, modeling errors, external disturbance, or measurement noise. So in the H infinity control, these are uncertainties are like represented by blocks that can be added in the system's transfer function. So what is the main objective of H infinity control is that we have to minimize the effect of these uncertainties on the system performance, which can be achieved by ensuring the system reject disturbance within the given uncertainty bounds. Now we can see sensitivity and complementary sensitivity function. So in terms of H infinity, so sensitivity means we already learned what is the sensitivity. So a lower sensitivity indicates that better disturbance rejection, which is the key aspects of the robustness. Means our system is robust, then it will be less sensitive with disturbance or noise or uncertainties. And complementary sensitivity means the function measures the system response, which can track the input in the H infinity control robustness analysis often involved. So main goal is like if we are minimizing the sensitivity function S, which can ensure the system sensitivity by minimizing the worst case condition and ensuring that the complementary sensitivity function remains within the acceptable bound to guarantee the performance. Now we can see robust stability in H infinity control. So in H infinity control, robust stability and robust performance are the key objectives. That is the motto for designing the controller design. So stability theorem, small gain theorem, and by using this we can also choose the system, and this should be like the left of complex S10. And in the small gain theorems, the and output. Model uncertainties and disturbance is not likely to destabilize the system. So uncertainty model. So if there is like uncertainties in the plant, which control robust stability and robust performance are achieved through careful design that minimizes the worst case behavior of the system in face of uncertainties and disturbances. So case studies of robust robust both stable, robust stability and robust performance in tracking and disturbance rejection. So how we can do? So we can design H infinity controller that can work. We minimize the worst case impact of uncertainties on the aircraft performance, and we have to also design the controller which can provide the robust stability by maintaining the desired robust performance of the aircraft and disturbance of exist. So like we can see individuals where we can see the applications of H infinity. So we can see like in aerospace and automotive engineering. So in the aerospace, it can use to enhance the stability and robust performance against the uncertainties, sensor noise and turbulence. It can also be used in missile guidance system to improve the trajectory, tracking and disturbance rejection. In automatic control, it can be used to adaptive cruise control, lane keeping systems and vehicle stability control. In H infinity control can also be used in robotics and mechanical mechatronics, in the robotics, it can use for precise motion of control under uncertainties. Means enhance the speech and audio clarity. In network control system, it can use to improve the stability under communication delays and packet loss. So now we can see residual use. Residual use. So now we will see what is the comparison in terms of handling the uncertainties and robustness. So the model uncertainties and external disturbances by making it robust against parameter variation and unmodel dynamics. LQR, so LQR can assume the accurate model and does not handle the uncertainties. Provides optimal performance only is more critical. Is more critical. LQR we can use in designs. So now we can see we recently asynchronous control are using. So asynchronous control is also extended for the nonlinear systems by using Hamilton equations. It also involves asynchronous control problem is LMIs, which can be formulated as a problem of the GiAN performance.
Thank you, Dr. Prajapati. Again announce the evaluations that we are going to conduct tomorrow to the participants.
Yes, sure. So tomorrow there will be a quiz at 7 p.m. and syllabus will be up to day 4. Okay, so all the lectures and PPTs have been shared over email to all the participants, and it is mandatory for to participate in that quiz. If you actually have participated in the quiz, then only the certificates will be issued and the credits will be given. Without the quiz, it will be, yeah, I mean, the certificates will not be issued. So this is mandatory for this particular GiAN course on resilient control of CPS. So I request every participant to please join in the quiz. So, and please remember the time is tomorrow at 7 p.m. Doubt, you can ask me or you can email me also.
It is just for the sake of information that the PPTs of today's morning sessions are shared with all the participants. And the PPTs of the afternoon sessions will be shared in the evening. Student volunteers, please make sure that the recording will still remain on during the discussions.
Our next presentation will be on fundamentals of cyber physical system and its application. Am I audible, Mr. Prakash? Mr. Prakash, am I audible?
Dr. Sauradeep, I just got a call from their end. He is going to join. So we can wait for 1 or 2 minutes. And if the participants have any queries related to the previous sessions, then I guess Dr. Prajapati is also here. So we can try to answer those queries. Dr. Saradeep, Mr. Prakash has joined the meeting. Can you coordinate the session, please?
Sure, Dr. So welcome, Mr. Prakash K. Today we'll have a lecture on fundamentals of cyber-physical system. This talk will be delivered by Mr. Prakash K from EduTech. So I request Mr. Prakash K to take over.
Yeah, thank you, team. Thank you, participants. Shall I share my screen?
Please share your screen.
Yes, it's visible.
Okay. Thank you. Yeah, thank you for confirmation. So, good afternoon, team. This is Prakash from EduTech India. I'm a manager on emerging technologies and the future mobility labs. So today, our key objective is what is CPS and what is the principles of CPS, the fundamentals, and what types of applications, and these are all the topics we are going to cover. So, give you a short introduction about the this. Maybe I hope you know that different types. Maybe I hope you know that different types of layers. When we talk about that industries of layers. When we talk about that industries, the hardware and the software have the multiple layers. Strategy layer and the fog and the cloud For example, in the industries, if you're for example in the industries, if you're using some controllers, sensors of that, you need to store the data. You need to store the data. You need to process the data in one through network. So all devices sync to each other. Then when we move to that, or we can say interconnected devices, and or we can say interconnected devices, and everything is small enabled. That means AI will be there in the edge level, and both physical and cyber digital data and physical devices can sync to each other, and we need to do the real-time data analysis decision making and we need to do the real-time data analysis decision making, and we need to improve the efficiency and productivity with the help of AI. This is all what is happening in industries as a smart industry, we can say. And the second one is both is possible, and also the drone aerial autonomous vehicle. So I'm going to touch upon the research with closely with our components, because we're also doing some form of research with some institutes, and we are offering this lab to all IITs, NITs, and the to cover up the computation part, or we can say think. When we talk about that think or computation, in the first application tree, one key robot in the smart factory is robotic arm. In the robotic arm, we need to do sensing. That means you need the sensors to see the thing and understand the thing, or we can say think. So in this case, in this labor or is synced to each other. That means in all the joints object, where is it? That means in the workspace, what is the location? From the robotic arm, what is the distance? You need to do all this computation. So this is what in the smart factory we are doing the computation part with the robotic arm. So here method is a formal method where you can do the image processing, and other method is using deep neural network, so that the basic image processing technique, we need to do all the calculations and we need to identify the suitable algorithm for different types of samples. In this case, for example, we can consider the label scanning. In this part, if you're using the basic image processing, you need to do the OCR. For that OCR, one thing, you need to train all the letters which format you are using. Then only you are the traditional OCR method is suitable for this application. But in future, suddenly if you change the label, then entirely you need to change the algorithm. But if it is a AI or 20 samples, then automatically it can train. So in the future, you no need to change the algorithm. So this time it's a label scanning. Next time I need to do that object segmentation. In this case, one object will be the circle and other object will be the square. So for this again, your OCR is not suitable. You need to change other algorithm to identify that from the color image to the black and white to that edge detection. From that you need to do some algorithm. Then only it can identify what object it is, whether it's a square or circle. The AI algorithm, the same DNN algorithm can use for different types. For example, you can hear the propeller sound, and it is doing that over. It is just take off from the ground to the TV level, and it is detecting the TV, and it will tell you this is the TV, and this is the backpack. And the left side you can see we are using real-time AI. That means it's not a pre-recorded video; it's a real-time. So the drone will fly. Parallelly, it can do the AI computing. That is what the power of hardware we are offering to the researchers. So this is one example for that computation for the drone. And that's two options. I'm just covering the concepts, the CPS, where you can see we are offering the 1/10 car, that is a indoor small size car with the NVIDIA AGX Orion board, inbuilt board with the RGBD camera, 4 CSI camera, IMU, and 2D LiDAR. It's equipped with sensor-rich devices. In the same thing, you can do the segmentation or lane detection using these types of AI algorithm, YOLO or the lane-led dedicated AI algorithm to do this types of research. And the same thing if you are doing the research on that controls. Previously, it's a computation. It may be the history of that smart mobility. I'm going to touch up both controls part. So when we talk about the controls for the robot, it's all about the principles here. The objective is starting from the right bottom imaging. There's nothing from the color image. You need to do that image acquisition and object detection. From there, you need to move the arm or you need to move the robot. So that's what the fault kinematics, and you need to do the result. One is stability control and another one is autonomous navigation. For this is example of our drone. We are offering this drone, and it is also sensor rich, where it's a NVIDIA CSI camera and RGBD plus time of flight optical flow sensor and 2 IMU. By fusing all these two, so this level of stability you can achieve it with solution. And if you're doing research on the controls, the concepts, you can cover it like starting from the basic mathematical model of the devices, and you can do the motor model. From there, you can identify the suitable parameter for the control, and you can change the control algorithm. It may be the feed forward, feedback, or PID, LQR, state feedback control, whatever it may be. You can change the algorithm, you can validate it. And also that indoor 1/10 car, where this is what the car, and with a smart map. Here you can see the smart traffic light. It can detect the traffic and it will open up the particular lane. Like if it is a huge traffic on one lane, it will open up that lane and it will close the remaining lane. This is what is smart infrastructure, where all devices, all car can communicate to each other. Each car know what is the current location of the car and the remaining car. Similar to that, traffic light also know all the data. If there is a 4 car, it know all 4 car location, nearby 4 car locations, and it depends on that, it will open up the traffic light. And the right side, you can see the digital twin. And the final part, we already completed the computation controls. Now it's communication. When we talk about the communication, this is one example where industrial robots, warehouse robots, they should navigate to that multiple obstacles, and all the devices should connected internally like a mesh, or either it's a centralized or decentralized. You need to communicate all the data. If there is obstacle, if you're going to apply brake, you need to share this data. What is the current your report, and the remaining truck. That means a 10 truck should follow the particular direction, and it will pick up the object and it will drop it somewhere in the industries, or it may travel through 100 kilometers, 200 kilometers, and with a limited control, enabled truck, it's making that human activity and less or comfortable, so that he can stay calm and he can monitor. So right on the right, you can see landing and takeoff from the moving robot. And the same way, robotic arm can also sync. Smart mobility, we are offering that, yes. Smart mobility, we are offering that, yes. Indoor car. So this is what that car looks like. I will quickly go. So this is what that car looks like. I will quickly go through the research. Academic people, how they are doing research. From University, Northeastern University, where they are using our indoor car with that cyber physical network analysis and design, and they are doing that application, and they are doing that applications like cloud-based systems, modern system, autonomous vehicle, pricing network, and a few more academic from Canada. So these all the outcomes from thing. You can do research, you can do the publications, and also you can achieve the conference. This is the paper. You can see using our small indoor car, you can replicate that.
Yeah. So good afternoon once again, everyone. So welcome you all in the lecture 12. So this lecture will be delivered by our eminent speaker, Dr. Souradeep Dey. So before he will start his lecture, I want to introduce him. So Dr. Souradeep Dey has received his BTech degree in electrical engineering from West Bengal University of Technology, Maulana Abdul Kalam Azad University of Technology, Kolkata, India in 2013. He received his MA degree in electrical engineering from Indian Institute of Engineering, Science and Technology, Shivpur, India in 2015. And he received his PhD degree in electrical engineering department from Indian Institute of Technology, Kanpur, India in 2023. He is currently working as an assistant professor in electrical engineering department, Motilal Nehru National Institute of Technology, Allahabad. His research interests focused on cooperative control, time delayed system and switch system. So now over to our eminent speaker, Dr. Souradeep Dey. Yes, sir.
Thank you, Dr. Prajapati, for introducing me. So today we'll discuss on introduction to time-period cyber physical systems and stability framework. So till now you have been familiar with what is cyber physical systems and what the analysis of time delays in the system. So how delays affect your system stability and how to mitigate the effect of delay or to prove that your system will be stable even if the delays are present in your system. So basically, I will go for a tracking problem to say what should be the effect of these delays in case of your CPS, and we'll show that how bounded tracking will be possible via some control estimator based architecture. And in general, these delays will have destabilizing effect in your system. So we'll consider a particular vehicle system, a multi-vehicle system, and there we'll check that if these delays are present in your system, so your protocols should be able to handle those kind of delays, and at the same time, they should have significant amount of performance in your MS. So this is a pictorial diagram of your CPS. So the design domain for cyber physical systems is this. These CPS are designed at the intersection of computing, control, and communication. The computing part includes things like microcontrollers, real-time operating systems, FPGAs, and these flash memories, and converters like your ADC or DAC, which are commonly used in embedded systems. And since these CPS often use sensor networks and communication between the processors, networking tools are important. The control part involves different control techniques, DSP algorithms, and real-time control methods. And most importantly, CPS are also spread across multiple systems requiring knowledge of distributed computing and control. So today we'll mostly discuss on this distributed control and how the delays will be there in the system. So these delays are actually unavoidable. Some of the decision variable. Now that decision variable can be position, that decision can be velocity. So it depends on the user's choice. Now we'll go for tracking. So in that particular case, I am having a dynamic leader in my system, and the objective is that all the vehicles will finally follow this particular leader. So this is an example for sensors. So this is the basic requirement, even if delays are present in your system or in the absence of your delays. Now, delays will come into your system. So, as interact with each other and they have mixed effect on your system. So normally these delays will deteriorate the performance of the system and may lead to instability. And the problem becomes more complex when they have the interaction of each other with each other, because effect in some other way. Now, if it is somehow possible that we can segregate the effect of these two kind of delays, then the problem will be easier to solve. This graph will be denoted as IK if node K receives information from node I. So now let's say you are having that n number of nodes, then you can actually find what should be my adjacency matrix. So edge weights are positive if the edge exists in the system, and if there is and based on our assumption, our assumption was that my graph will have a rooted directed spanning tree. Based on this assumption, so this n number of agents will follow so this n number of agents will follow a general trajectory, and the thing is general trajectory. And the thing is that this general trajectory or the reference trajectory is not fully known to all agents. And delays are two kind of delays are present in your system. One is communication delay, which is more significant in case of your CPS. And also due to the processing of my agents, there are input delays are also present, and these are heterogeneous in nature. So we'll go for a dual layered architecture where an estimator will be system. So, okay, one more thing is that as the number of communication links is grow on in, so in this particular that any position in the airplane, and you have to develop a controller such that they will finally converge to the desired trajectory. Now, why this is coming as ultimately bound minus tau to 0. Now, the solution of the xt of these systems will be uniformly ultimately bounded if there exists a beta greater than 0, such that for any alpha greater than 0, there will exist a time t, which will be a function of alpha, will be greater than 0, such that my solution, the absolute value of my solution, will be less than equal to beta. Quite mathematical. So let it make it easy that, let's say, the error between the desired trajectory and the actual agent states will always be bounded in range. So as we have told that I will have a tracking controller part and a estimator part, right? So what is the function of this tracking controller? So in this particular case, you just see here, this is my agent dynamics. So this involves because we want that my communication link should be as low as possible. So this is the xi plus 1 hat t that is coming from I plus 1th agent, and this is the velocity of I plus 1th agent estimated state. Now there will be a communication delay. So this is my delayed value of my position estimated position of I plus 1th agent, and same for the velocity also. What we are doing in this particular case, this xi hat t, essentially we are taking the delayed value of own state, and here due to the practical consideration of this xdt and xt dot. So now I have to make sure what should be my, let's say, ensure bounded traffic. So though it is known to me, because by taking the GI hat dot t instead of this xt double dot t leads to a decoupling among the individual agents in terms of the condition on control gains and input is required to ensure bounded traffic. So this is just for the easiness of solving where we want to segregate the effect of delays. Now, let's say we are defining the error variables like this. This is my desired trajectory, velocity state also. And what about these two states? This is the difference between actual agent states and the estimated states. So you just see here, if these error variables goes to 0, then finally, and xi hat t is, let's say, towards xdt, then finally xit will be equal to xdt. Similarly, for the vit will be xt dot. That is the objective. So exactly we can do that because we don't have the future information of the cell. So characteristics polynomial, and at the end, this is the characteristic equation. At the end, this is the characteristic equation of your system. Now you just see when AID equal to 1, that means the information of the desired trajectory is particularly coming to ith agent. Then we just have to ensure that this particular factor have negative real parts. The roots of this will have to have negative real parts. That is just possible for positive values gamma iv and gamma iv. But when the information of the digit trajectory is not coming to I present, that time I have to ensure that this particular factor will have negative real products. And after calculation, that if your communication delay is bounded by this particular term, then your estimator will be stable. So in this particular case, after derivation and SI, these matrices are positive definite matrices. Why? Because I want that energy to be positive. So this matrices should be positive definite, this should be positive definite, and this matrix should be positive definite. And I have to satisfy this WI, these are the plus A infinity function. So after mathematical derivation, that is a long process, so I'm not going through the derivation. You can finally prove that difference between the XD and XI, and here also XD dot and PI are going to be uniformly ultimately. So that is one kind of estimator structure we have shown. Now let's explore different kind of estimator. So actually the estimator structure will take care of your communication delays in your system. Now you can come up with some novel kind of estimator structure also, by which you can make the delay margin single integrated estimator. You can have the Laplace transform, and after that you can find what should be the characteristics polynomial, and from that you can find what should be the delay margin. And in this particular case, you can see that delay margin is same for both the design, that is design 1 and design 2, and that will be feasible if this LMI has a feasible solution. So while we have, so whenever we are going for these two kind of designs of the estimators, now it is important to analyze which one yield better delay margin. So let's say FI1 is the delay margin for design 1. So this value we are telling that say this is FI1, that is the delay margin based on the estimated design 1, and this is FI2, that is the communication delay margin based on the estimator design 2. So theoretically you can prove that this shaded region, that yellow color region, in this particular case, FI2 is greater than FI1. So whenever I am having this coupled single integrated estimator structure, that will yield better delay margin compared to the double integrated estimator structure. So what is that condition? That is either CIP should be less than equal to CIP, so this region, or CIP less than equal to pi by 2. So this is this region. So this is sufficient condition such that your second integrated estimator yields better delay margin. So is it like that? Then always we go for the second integrated, the design 2, that is the coupled integrated based estimator structure. For that, I have to exactly find what should be the segregation region, and that can be done using numerical methods. So here you can see that suppose for a given CIP greater than, so why we are taking CIP greater than pi by 2? Because we now want to have, because in this particular region we have to do that FI2 is greater than FI1. So the remaining portion left is the white one, which is not unshaded region. So in this particular region, our objective is that on which spaces that delay margin of design 1 will be greater than design 2. For that, you will finally solve, you will get one particular CIP equal to CIP star. So graphically, you can see, let's say at this particular positions at CIP equal to CIP star, you are having both the delay margin to be same. So that will represent that both the estimator structure have the same delay margin around this curve. And the green shaded region means your design 2 will be better, and the blue shaded region means the green shaded region means design 1 is better, and blue shaded region means that design 2 will be better. So it depends on what are the possible values of your delays in your system. Based on that, you can choose which estimator to select. Okay. So normally it can be found numerically that the maximum margin on the communication delay in this particular case has been given by this particular value, let's say 0.3490. So now we'll go for the heterogeneous delay simulation. So let's say I am having 4 agents in my CPS, and this is the feature trajectory that is given by 1 plus t plus I. So this is the initial values of the position and velocity of the agents. These are the input delays, and these are the communication delays. So we want to have a comparison like that, which estimator structure is giving the performance better or worse. So for that reason, I am taking identical set of design parameters for both the design. So this controller gains how can design based on the thing. Like here, from here you can find out what should be the controller gains, and from this stability condition you can find out what should be the estimator gains. So satisfying that stability criteria, we can choose this particular values. So normal basic thumb is that don't go for values which are very marginal. I mean, let's say on the verge of instability, if you are taking some estimator gain or controller gain, in that particular what will you see that the system is stable, but it will have as a thumbnail, like let's say in between, let's say 0 and that particular threshold. And for agent 1, which has the information of the design trajectory, we just select the gains like this, gamma 1p and gamma 1b. So here xi is the position and vi is the velocity. So you can see here that the agents finally follow the desired trajectory. The red color one is the desired trajectory. This is for the estimator of the design 1, and this is based on the estimator design 2. So similarly, velocity profile can also have been plotted here, and you can see, of course, both the design when it satisfies the stability criteria, tracking is possible. Now it is, of course, bounded tracking. You can see from here also that that red colored one is the XT tolerance. So there is little bit gap between the agent states, agent's velocity states, and XT tolerance. Similarly, that is true for the position also. But our objective is that I have to ensure bounded tracking. So let's say one vehicle is moving, that is the reference vehicle, and the other vehicles will try to follow that particular vehicle with some, let's say, deviation. So it should not be outbound mode. So that means it should not happen that there should not be continuity gap like that one vehicle is moving towards some different direction or something. It should follow that particular direction. So based on this, we can have this both the design 1 estimator and design 2 estimator, and ensuring my system is having bounded tracking. So let's see that if we compare with some other works which consider only controller-based architecture. So, in general, if you have this input delays in your system and communication with let's say 20 number of agents. So, and let's say you are having double integrated dynamics. Then the size of the LMI will be huge because the LMI of because this time it is not the LMI of individual agent, rather it is the LMIs of the complete system. So whenever I am telling complete system, that means that system consider 20 number of agents together. So you have to find out consider 20 number of agents together. So you have to find out the state space representation of 20 number of agents that complete matrix will come in the system. So that total system will have been ensured stability based on the feasibility of LMI. So if you go here, what we have done for the LMI in this particular case. So yeah, here if you go, you can see here the LMI I am doing for the tracking controller gains only. So for the tracking controller gains, I am having that system and be not to be the complete system. It's the individual agents only. So let's say I am having this double integrated agents, that means it's a second order system. So I don't have to go account for the n number of agents, 20 number of agents. So that the advantage of this is that I don't have to deal with the big, large LMIs. So solving our large LMIs is actually problematic. I mean, finding the physical solution, because at the end of the day, you have to find a physical solution, and there exist conservative results also. So more practices are there how to found this particular Newton-Krasowski function or the Rajanikhan theorem such that you can reduce the conservatism in your system. So I can design some kind of Newton-Krasowski, but it is very much conservative. So of course, if the feasible solution of that particular inequality exists, you will have the solution. But what is the guarantee that the feasibility of that matrix will be satisfied? So that's how the conservative will come in your system. So it is wise choice to make the LMIs of smaller size, and mostly we can get a feasible solution. So there is no guarantee. So based on the system's architecture, these LMIs will have the different kind of delay margin in your system. So yeah. So we are here. So the stability condition is obtained through a feasible solution of a large LMI that I have told, which involves the coupling between input and communication. And you can see in the simulation here. So we have, let's say, this is the tracking position error, and this is the tracking velocity error. Okay. So this is if the input delays and communication delays interact with each other, then we will get this kind of solution. Of course, in this particular case also, you can ensure boundary tracking, and this is for the velocity profile. And this is based on the estimator-based controller architecture. Of course, we go for the boundary tracking. You can see here, in terms of the error difference, this graph is outperforming the past one, because in this particular case, we have actually segregated the effect of delays. So, what could be the possible extension? Like in this particular case, let's see, I have considered constant delays. Now the delays can be time varying in nature. So in that particular case, Newton-Krasowski functional, whatever we have designed for, we have to modify that, because that time not only the values of the delays, but yeah. So not only is the value of the delays, but what should be the upper bound of the tau by dot t, that will also be significant. So based on that, we have to modify the Newton-Krasowski functional, and we have to go for the stability analysis of that. So several criteria exist there: Jensen's inequality, so regular cycling. So there are several methods by which you can solve those particular LMIs, and research is going on in this particular field also. And one more thing is that from where we have started. So we actually discuss more only on this distributed control. Now, whenever you have to implement that on a real-time system, that time is real-time control will come of the rigid body dynamics also. So you have to go for the collision avoidance protocol such that none of the agents interact with each other, none of the agents collide with each other. So those kind of systems will be there. So the primary is the, let's say, low-level control. After that, this kind of distributed control will come into the system. Wireless sensor networks all together will have a complex scenario. So that's why whenever you are calling that a CPS, cyber physical system, we have to consider all the three aspects, that is the computing design space, control design space, and communication design space. So those who are interested in the communication part also, they have to consider what is that packet loss and everything that should be plugged into your system. So you will see that whenever you are actually working in this complex system, so many aspects are there in the system. Of course, trade-off will be there. So here in today's lecture, we have talked about only one aspect, that is the time delays in your system. So many aspects will be there in your system. So sometimes you will have the unmodeled dynamics in your system. So how to get rid of that? So that area, that's why is reverse building. So yeah, that's all. So if you have any doubt, please ask me. So if you have any doubt, you can ask me now, or my email ID is saradipday@mnnit.ac.in. You can mail me. I will be happy to answer your queries. Thank you.
Dr. Saradip, thank you.
Thank you, sir.
And on behalf of the participant, I request you to please share your PPT with us so that the same can be shared with the participants.
Definitely, we'll share the PPT, and I think they'll get it by today's evening, so that they can prepare for tomorrow's quiz, which is actually essential for them to get the certificates.
Yes. So I believe all the sessions of day 4 have been concluded successfully. So if there are no further queries from the participants' end, then we can conclude the sessions over here. And tomorrow the session will start at 14 hours IST. So I request the participants to join before time. And I repeat again, although the Dr. Day has sessions,